Hello and welcome to what has possibly been one of the most exciting weeks of my life. Just a few days ago I was walking on top of a B-58 Hustler, crawling through a B-36 crew tunnel, and today I'm sitting here in the cockpit of a Lockheed SR-71 Blackbird. This was a top secret reconnaissance aircraft capable of Mach 3.2, and as a child I had a poster of one of these on my wall, so you can imagine how excited I am to be sitting in here. Now in this video I'm hoping to make this the most detailed tour of this aircraft on YouTube, so it's going to be a long video, so let's get into it. I'm Paul Stewart and I make videos about planes and some music. And more music. This includes onboard flights from around the world and guided tours through significant aircraft and museums. If you're into these types of videos, then please check out my channel and subscribe. And a massive thanks to the Evergreen Aviation and Space Museum near McMinnville, Oregon for letting me film inside this aircraft. It's a great museum and they've got a huge range of aircraft on display, including the only Hughes H-4 Hercules, also known as the Spruce Goose, which you can take tours inside of. While this video is going to consist of me mostly crawling around this aircraft, we really should begin with some history. When the Lockheed U-2 first flew over the USSR in 1956, they returned with valuable photos, but of concern, they had detected Soviet radars during the entire flight, dashing their theory that they could fly over enemy radar systems. Thankfully for the Americans, the Soviet Union was able to watch the U-2, but they did not have the missile technology to shoot them down, yet, and the Americans knew this, so the following year, the CIA asked Lockheed to build a new spy plane that would become Project Archangel, to make a secret jet that could fly faster and higher than missiles and be invisible to radar, and that became the Lockheed A-12 Oxcart. The letter A stood for Archangel, and the number 12 came from it being the 12th design proposal. Now every avgeek knows about the high speed, but what's often overlooked is that this really was one of the first stealth planes, which I'll explain as we look around the SR-71. In February 1960, the CIA agreed to buy 12 of the A-12 aircraft, and only several months later, Francis Gary Powers was shot down over the USSR on board a U-2, highlighting the importance of the new plane. This also shows that the Archangel program was not in response to the shootdown and was already well under development. In fact, it's normal for the replacement program to begin while the original aircraft was still either in its late development or early introduction. In fact, you might recall in my B-58 Hustler video from a few weeks ago, where the program was beginning while the Boeing B-47 was barely flying. The A-12 first flew at Groom Lake or Area 51, Nevada on the 25th of April 1962, and 13 were built. There was also two M21 motherships, which you can see here in my video filmed at the Museum of Flight in Seattle, and these carried D-21 drones. There was also the YF-12A interceptor prototypes, and I filmed a video around the only one left at Dayton as well. Of interest, the YF-12 interceptor had a unique nose due to the fire control system radar, and they could carry AIM-47 Falcon missiles. It's unclear how serious the program ever was, as there's an idea that it existed purely as a cover story for the then still secret A-12 spy plane. If there were photos of the A-12 captured, the CIA could simply say, oh, that's just the interceptor version, nothing to see here. In December 1962, the USAF ordered their version, called the RS, standing for Reconnaissance Strike 71. When President Lyndon Johnson announced the existence of the aircraft in 1964, he called it the SR-71, while the print versions of the speech sent to the media said RS-71, but they decided that the SR-71 sounded better and no one wanted to correct the president, so they stuck with that. The 71 number comes from Kelly Johnson trying to promote a bomber variant. Because this came after the proposed B-70 Valkyrie, they went with the next highest number, making it the B-71. While that did not get past initial drawings, the 71 number stuck, and the Blackbird name came from the distinctive black paint. It was different from the A-12 Oxcart, and here's a diagram directly from the CIA. The SR-71 was 6 feet longer, weighed 15,000 pounds more when fully loaded, had 2 crew members, a more prominent nose and chines, and could carry additional optical and radar imagery systems. The SR-71 first flew on December the 22nd, 1964, and in total 32 were built. Let's check out this incredible example here, starting at the nose of this sleek and sinister looking aircraft. As we know, high altitude was no longer a main defense from Soviet attack, and instead it was high speed. While any missile or interceptor was no threat from behind, as this could simply outrun it, attack from the front was a potential risk. Therefore, this device down here was the radar warning antenna designed to identify incoming radar waves and missiles. And then moving back behind that was the transmitting antenna from the electronic counter-measuring equipment. Essentially what these systems did was to confuse the enemy locating radars from both ground stations and the missiles themselves. They might identify the incoming radar signal, and then modify it, and then send back incorrect information. Other systems included overwhelming the radar receiver by returning a high amount of the same frequency, scrambling their screens. Ideally, this would confuse and divert off any missile coming from in front. This is a vent here for the cooling air pumped into the nose cone to keep the internal equipment cool. You'll see a line along here, and this was a modification that came after the A12, where they could simply disconnect a nose cone and install another one, all in about 45 to 60 minutes, just unscrewing 4 bolts and connecting a few cords. They would also be full of electronic equipment, and they themselves would be heated by the aerodynamic heating from being at the front, hence why cooler air-conditioned air was pumped in here to stop the equipment from cooking. Looking under here, and there's a whole array of sensors, including where a periscopic view sight for a second crew member would have been positioned, before likely being replaced on this example. Obviously, with their position being behind the pilot, they otherwise would not have been able to see anything forward, as we'll see once we jump inside, although there was a B model which did address this problem, and I'll mention that again later. Let's check out the nose wheel, and you'll notice that the rubber is black. I'll explain more at the main landing gear, which you'll notice is silver, but the nose wheel were able to survive the aerodynamic heating from the Mach 3 flight because the wheel well was air conditioned from the exiting pressurized air from the cockpit. This is why there are these vents here, to allow the air conditioned air out. Looking up into this incredibly well presented wheel well are silver nitrogen tanks. This was used to inert the fuel tanks, so that after the fuel was used up, this was pumped in to fill the space that was left. Once they ran out of this, they would have to limit their speed to Mach 2.6, and later on another tank was added to improve the Mach 3.2 range, where the fuel itself could be heated to up to 300 degrees Fahrenheit. One of the reasons why this was such a great museum is because the access hatches are open for you to peer into. On the port side in this electrical component bay was the removable battery, circuit breakers and other electrical systems, while on the opposite side was the radio bay where communication and navigation equipment would be located. And then next to that is one of the many mission equipment bays that run along the underside of the chines. Here's older footage from a previous visit where you can see one of the ECM devices and how it would simply be hoisted up into the equipment bay. This design made changing all of the equipment an easy and quick process. Walking further back to the next and closed port side equipment bay is where the technical objective camera would be positioned, with the lens looking out through the glass section. Now here's the camera on the outside, and check out the size of that film there, as it's 5 inches wide and over 10,000 feet long for the poor analyst back at the base to look through. And then at the other end of that is the part which looks a bit like a periscope, and that's what would be looking through the glass that I just showed you. These were highly classified, and this is one of only not many remaining anywhere in the world because the rest were destroyed so that they could not be stolen and copied by the enemy. Moving on, and let's talk about the chines, which were revolutionary for the time, as was many design aspects of this aircraft. These lateral extensions of the fuselage run the full length from the nose right back along the fuselage. They have a number of advantages, including generating lift, especially at high altitude where the much thinner air is more challenging to work with. It's also an early stealth design, as the shape minimizes the corner reflections or vertical sides to radar waves, therefore reducing its radar cross-section. It also has created ample storage space for equipment, just as what I just showed you, leaving the center of the fuselage for the crew and the fuel. One of the major design challenges with this aircraft is the aerodynamic heating. At those 2,500 miles per hour, the particles in the air would hit the plane surface so hard that they would generate a lot of heat, with some parts of the SR-71 skin reaching 600 degrees Fahrenheit or 300 degrees Celsius. This heat would then be transferred throughout the whole plane. Standard materials simply would not survive the temperature, therefore titanium was used for 85% of its structure. The problem is that this had to be sourced from the USSR, so the CIA set up fake companies in other countries, shipped the titanium there, and then covertly onto the United States to go into this aircraft. Then the idea was that the same titanium would again visit the USSR at a much higher speed. The fuselage would expand and contract as it goes through the major temperature changes, and allowing for this expansion was engineered into it, hence why you can see this expansion joint here. The engine had similar complications. In fact, you can see similar expansion joints and corrugations in the piping to allow for the thermal changes in the engine, which we will look at in more detail later. Even the flight control cables would change size as the fuselage heated up, so engineers had to allow for that. It really was an incredible design. We will follow the chines as they form the wings leading and then lateral edges, and we'll sneak past the inlet spike and engine and talk about that on the other side. The wingspan really was quite small, especially when compared with other high altitude aircraft like the Lockheed U-2 I mentioned before, and later versions of the Martin B-57, where the wings were even extended further. What compensated for the smaller wingspan were the chines and the shape of the fuselage, essentially making it a bit like a lifting body where the whole fuselage generated lift itself. Another stealth design feature was the use of radar absorbing materials. If you look closely here, you'll notice the sawtooth shaped triangular panels, and these were radar absorbent materials. Like later stealth aircraft, the shape was important in avoiding reflecting radar waves, but if they did reach the skin, then the surface themselves would absorb the waves rather than reflect them. Looking at the wingtips, and you'll notice a slight conical camber, and this was because during testing they found it improved stability during cross-wind landings, and it seemed to reduce drag at supersonic speed as well. The paint itself had iron particles in it which again absorbed the radiation. We will come back to the tail section, so let's move in and have a look at the main landing gear, which consists of 3 tyres per strut. Unlike the nose wheel, these are silver, and that's because the rubber was infused with aluminium particles, which help reflect the intense heat generated by the aerodynamic heating. Remember that the nose wheel well was cooled by cabin air conditioning, but this wasn't, hence why it would be hundreds of degrees Fahrenheit inside. The gear strut itself was milled from a single solid block of titanium, and that was to manage the intense pressure from the high-speed landings and takeoff. Looking up into the wheel well, and you see that the tyres fold up into this metal object called a can, which was designed to insulate the heat, but also contain any potential tyre explosions from the important hydraulic lines nearby. The tyres were inflated with inert nitrogen up to 400 psi to help manage the intense stresses, and for comparison's sake, your car tyre is probably around 36 or 38 psi. These were only rated for up to 15 flights before being replaced. On the way over to the start cart, let's quickly look at the inlet spike, which I'll mention in more detail on the other side when we have a look at the incredible J-58 turbojet engine, but let's just have a quick look inside the nacelle, and sorry for the focus problems, but these bulges here were known as mice, and they were positioned directly behind the boundary air removal device. These were designed to generate controlled turbulent air ideal to enter the engine, as opposed to less predictable turbulent air before the mice were installed. Let's talk about how these engines were fired into action. Now I found out after filming that the circular panel here was for access to the hydraulics, so you'll just have to use your imagination for something similar but elsewhere, which is where the start cart would attach. At the time, air starters propelled by compressed air just weren't big or powerful enough to start this massive engine, so instead they stuck 2 Buick 425 cubic inch V8s sharing a drive shaft that would then be attached up to the J-58 engine via a gearbox. Apparently production of those motors stopped in 1966, so the Air Force bought up every second-hand one they could find, but eventually they were replaced with Chevy V8s as supply was impossible. Not that I'm a biased Ford man or anything, but I did wonder why they just didn't use a more powerful and generally wonderful Ford V8, because they'd only have to use one of those and they'd be perfectly reliable because, as we know, Ford stands for first on race day, oh, so I'm told. I reckon they sound better too, and of course that's got nothing to do with me regretting selling my old XR8. This shaft here on top would plug directly into what's behind the circular panel you saw earlier. They would run the engines up to around 6,000 RPM, which would correspond to around 3,000 RPM on the J-58, because of the gearing. Then the pilot would increase the throttle on board, which would then bring it up to its idle speed of 4,000 RPM. Apparently the story was that the ground crew might sometimes get excited by the noise of those V8s and not disengage it, so they would overstress them until failure, hence why they started to run out of them. Later on, they used far simpler and lighter air turbine starters, which you can see here, and you can see that they have an identical attachment. These relied on compressed air or any politician standing nearby, and both these and the V8 start carts produced around 700 horsepower each. This down here was the brake cooling fan. Because of the high landing speeds and the large size of the SR71, the brakes and wheels would be very hot by the time they pulled into the ramp, so the crew would use these brake cooling fans to help dissipate the heat. And here's a quick glance at some of those tyres impregnated with aluminium particles. You can actually buy these from the museum, with proceeds going to support the incredible and expensive job of maintaining these aircraft for future generations to appreciate. Let's go and check out these incredible engines, and I have to give a special mention to Arne Gundersen and the AirZoo YouTube videos for some of the information I'm about to share with you. Within the intake is this conical spike, which would move 23 inches back at high speeds to optimize the air entering the engine. At low speed, you would want as much air entering as possible to feed the thirsty engines, but then at supersonic speed, the air would need to slow down as to not damage the engine, so this spike would modulate the air depending on speed. This display is especially fascinating because the nacelle has been opened up so we can have a look inside. The engine itself started out as a project for the Navy, although they eventually lost interest due to concerns about the cost, and instead the CIA approached Pratt and Whitney about using it in their future reconnaissance plane, and that's what you have here. The job description was pretty challenging because it had to cruise at Mach 3.2 at high altitude. Looking forward briefly, and you can get an idea of how long the nacelle is, and how far behind the intake spike the engine was actually positioned. Now let's zoom in closely and discuss a few aspects of the single-spool Pratt and Whitney J-58 turbojet engine that could produce up to 34,000 pounds of thrust each. You'll notice a cross marked on one of the turbine blades, and this is because after every flight, they would use a bright light to inspect the first stage compressor blades. If there was a new nick on any of them, then the outer wing would be swung up like we see here, and a borescope of the compressor had to take place to ensure that there was no further damage internally. There were some very slight mechanics who could crawl inside, but otherwise this inspection was all done from the front. The cross is to provide the crew with an endpoint so that they knew that they would have finished inspecting every blade. The limiting factor with the aircraft's speed was the temperature, therefore there were multiple devices at the front of the engine to identify the inlet air temperature. This thick object here tells the afterburner system the inlet temp so that they can modulate the fuel flow there. This probe here identifies the inlet air temp, and that information is sent to the cockpit dial to inform the pilot, and I'll show you that shortly. These two essentially catch helium gas, which is known to expand uniformly based on the temperature, and that can be measured giving the engine an accurate temperature reading. There's two of them to provide redundancy. Underneath the engine was a gearbox and a drive shaft that would connect to here and to the accessory drive system, which would power the electrical and hydraulic systems of the rest of the aircraft. I'll show you where this connects to when I stick my head inside the nacelle shortly. Now this under here is where the Buick start cart drive shaft would attach in as well to start the engine. Now all of these pipings are associated with the computer management system. Digital computers remained quite new, too large, and wouldn't stand up to the excessive heat from the engine, so this spaghetti bowl of piping was all associated with the analog control system. The piping all has either fuel or oil inside of it, so the fluids actually worked as heat sinks and reduced the temperature of the piping. Fuel throughout the aircraft was actually pumped around and used to lower fuselage temperature, similar in principle to the car's radiator fluid. Now there are hints of gold on certain components, including this fuel oil cooler here. They found that it did decrease the temperature of the object, but the cost wasn't really worth the effort, so you can see that when the gold covering partially wore off, they didn't bother maintaining it. This up here contains TEB, which stands for triethylborane, and I'll come back to that shortly. The SR71 used a special fuel called JP7, which was extremely stable, would not vaporize at high temperatures, as the fuel tanks would be a few hundred degrees Fahrenheit, nor spontaneously ignite. In fact, there were stories, which may or may not be true, of where they would give apprentices a shock by smoking around barrels of this stuff and throw a lit cigarette into one of them. This was so inert that even the lit cigarette would simply be extinguished by it. So to actually get the JP7 to ignite, they had to use this substance, TEB, which would be sprayed in whenever the engine was ignited and the afterburner ignited. This was extremely fragile and would ignite when exposed to the atmosphere, so the ground crew had to be extremely careful around it. You can see this line here from the TEB container to the burner can where it would be sprayed in. You've probably heard stories of fuel dripping onto the ground underneath the SR71, and that's because it used a wet wing design where fuel was stored directly within the fuselage and wing and not within separate tanks. So the fuselage's skin was also the fuel tank skin. And because the skin would expand and contract with the temperature changes, the fuel was able to leak out once the panels had contracted. But this was not a problem, as I said before, as the fuel would not ignite without the TEB. You may recall that the fuel tanks were inerted with nitrogen gas, so you may ask why, when the JP7 itself was so difficult to ignite. The reality was that it was probably, 99.95% safe for the tank to sit full of JP7 vapor and oxygen, but no one wanted to take that risk, considering how hot the fuselage would become, so the nitrogen system was used. Running along the side of the engines are bypass tubes moving air from the rear of the compressor to just before the afterburner. These were installed after testing a Mach 3 revealed that the forepart of the compressor was actually getting starved of air while the aft part was getting congested. So they installed these tubes that bleed air from the congested aft compressor from around Mach 2. Instead of dumping that air outside and losing all of that energy, they decided to tunnel it back into the engine just before the afterburner and ready to be ignited there. This provides extra momentum and also has the added effect of cooling the tail end ever so slightly as it did bypass the hot core. It's also interesting to note that the thermal expansion also affects the engine. In fact, it grows around 6 inches in length and 2.5 inches in diameter at Mach 3 cruise. So you've got these corrugations in the pipe here to help manage that. Towards the aft end of the engine and near the afterburner, its skin could be up to 2000 degrees Fahrenheit, which is pretty incredible, hence why it appeared like this during afterburning testing. These here are the actuator rods for the adjustable nozzle pedals that we'll look at shortly, and these thick pipes were supplying the fuel to the afterburner. Looking at the back of the engine, and if you look closely at these light coloured flame holders, and the fuel is pumped out just in front of those. TEB is used to ignite the afterburner as well, although it's still just injected into the same burner section of the engine, as the TEB flame can pass through here and ignite the afterburner fuel as well. If they did run out of TEB, then those small circles there are catalytic igniters made of platinum, and the pilot could manually increase the exhaust gas temperature, which would make those glow hotter, and then they themselves could ignite the JP7 that's being sprayed in. When we're in the cockpit, I'll show you the control for that. The lining of this section is a nickel-based alloy that is highly resistant to heat, although it's also covered with a ceramic coating to help manage the high temperatures. You can see that it's lined with holes, and these will all have cooler air blowing through that has bypassed the engine and that has been sucked in via the doors on the sides that I'll show you shortly. Now this is a convergent divergent nozzle, affectionately called the donut by engineers, and it's hard to see until I walk over towards it, but it's slightly larger than the entire J-58 engine. Now we have to remember that only 1/3 of the air that enters past the nose cone actually goes into the turbojet engine, and 2/3 simply moves around it. The forward motion of the plane compresses this bypassed air, and instead of letting that air be discharged out to the side and lost, they squeeze it back into the exhaust via this donut so it adds to the total thrust. This is essentially acting like a ramjet engine once they're flying at Mach 3.2. In fact, they say that at that speed, the hot core only produces 20% of the thrust, while the rest comes from the air bypassing it. Of interest, during the process of being pressurized, as it enters through the nose cone but bypasses the engine, it slows down to subsonic speed but heats up to 1000 degrees Fahrenheit. But remember that this is relatively cool, as the engine itself can be over double that temperature, especially towards the end, so this relatively cool air actually works to cool the engine. It's all pretty amazing stuff. You've also got these doors here, which can suck in further air from the atmosphere and add it to the fire. Behind the donut are these turkey feathers, which were part of the airframe rather than the engine, and these could modulate the thrust by adding pressure by narrowing the exit. Let's step inside and go somewhere you've probably never seen before. It was pretty incredible standing inside the nacelle of a real SR71, knowing that where I was, a J-58 engine had been powering this along at Mach 3.2. The noise and air rushing around in here would have been impressive and extremely hot. As I said, the JP7 fuel was used as a heat sink, and what's interesting is that when the fuel got low, there was less to dissipate the heat, so the whole SR71 would be noticeably hotter. The relatively cold fuel from the in-flight refueling would then provide some cooling relief to the crew. In fact, during emergency landings, when the tanker was unable to top them up, they might land with the cockpit far above the recommended temperature limits. Following the last refueling, they would often fly much slower for the last 45 minutes of the trip so that the aircraft was cool enough for the crew to get out and the ground crew to avoid getting burnt touching the surface. Otherwise, they'd all have to just sit there and wait for it to cool down spontaneously. This tube here on the right was the engine air bleed for the cabin pressurization. This very hot air would be cooled to cabin temperature for the crew and then expelled through the nosewheel like I mentioned earlier. Stepping back and down here, you have this shaft that I mentioned before attached to the underside of the engine that powers the electrical and hydraulic systems. Of interest, these parts of it here were to allow for the thermal expansion as the engine heated up and cooled down. This down here, and it's partially obscured, is where that shaft would connect into the accessory drive system. And above that, you're looking at the intake spike from behind. You can see those little mice that I mentioned on the other nacelle. Turning around and sweeping past the J-58, and you can see the donut again that would be forcing all of the air together and generating more thrust. The SR-71 holds the official speed record for a piloted operational jet aircraft of 2,193 miles an hour or 3,524 kilometers an hour and an altitude record of 85,069 feet. The faster A-12 Oxcart unofficially but still documented max speed of 2,208 miles an hour at 90,000 feet was reached during testing in 1965. Having said that, there are unconfirmed reports of both beating those records, so it's hard to say, but we'll all agree that it was very fast. Let's make our way underneath the tail and go and have a brief look at engine number 2, well the nacelle of it, giving you a bit of an idea of how large this aircraft was. Looking again at the turkey feathers, and it highlights how these are just part of the airframe rather than the engine itself. On many other aircraft, these would be attached to the engine when it would be removed. As you can see, it's empty inside, other than the nose cone, and there are those suck-in doors that I mentioned on the other side that were spring-loaded, and they could allow in additional air. Now I know this is a little out of sync as I spoke about the history earlier, but the whole program was done in complete secrecy. In fact, they only allowed married men on the developmental team because they believed that they were less susceptible to attractive Soviet spies. When it was transported from Lockheed HQ to Area 51, they put it inside these large containers on the back of a truck to avoid it giving away its shape. Unlike most aircraft of that era, it had a large and relatively flat underside of the fuselage, which acts somewhat like a lifting body, but importantly, it also reduces the radar cross-section, as many of the radar waves will deflect off it in another direction as opposed to reflecting directly straight back at the receiver like on a regular rounded fuselage. You see this similar idea in the stealthy F-117 and B-2 Spirit. Apparently this shape reduced the radar cross-section by 90% over previous Archangel design proposals that had more traditional shapes. Now it's worth mentioning the two vertical fins. By having two smaller fins instead of a single larger one, you're keeping the whole aircraft lower, allowing for easier storage in the hangars. There's also redundancy if one of them were to fail or be damaged, and by angling them slightly inwards, they would have a lower radar return than a regular 90-degree tail. As I mentioned earlier, this really did have many stealthy design techniques, so maybe we should be calling it the first American stealth fighter, even though it's not a stealth fighter, just like the F-117 strike aircraft wasn't as well. The orange object is a parachute, which would have been released from on top of the fuselage, following touchdown to help slow down the plane and avoid cooking the brakes. This here right at the end of the tail was the ventral fuel dump valve that could be used if they needed to urgently land while overweight. It could also vent excess fuel if they overfilled it, or other fluids that might have built up in the fuselage. Here you can actually see some fluid escape as it accelerates forward. Now let's have a look up here at this system. And those pipes that you can see here carry the fuel to the tail to be dumped. The rest of it here is the mixer assembly that was an electrical and mechanical system that took the flight control input from the pilot and then sent it out to the control surfaces. These springs were used for artificial feel so that the pilot would feel resistance, which was especially important at higher speeds to avoid them accidentally overstressing the airframe with dramatic control surface movements. As we walk our way forward to check on the crew positions, I'll mention that if you enjoy these videos, then please consider becoming a channel member. These videos take a long time to prepare, especially when I'm not based in the USA, so your support helps me make more of these and avoid product placement. I understand that the finances might be tight, and that's totally fair enough, but please give the video a thumbs up and comment to support the channel in that way, as it's totally free. As we know, this would cruise at Mach 3.2, which is around 2,200 miles an hour at 80,000 feet, but an important part of that is that I'm talking about cruising. Not just a brief Mach 3.2 during a dive or evasive maneuver, but this would sit with cruise control at that speed, only really needing to slow down to refuel, as the KC-135s would struggle at that speed, or so I'm told, although I'm sure Tex Johnson would have given it a try. Of interest, because the A-12 was operated by the CIA, the pilots had to resign from the USAF, and were then re-employed by the CIA. As the later SR-71 was operated by the USAF, it had their markings, and the pilots were still USAF and carried Geneva Convention identification cards. Now let's check out the two crew positions. In front is the pilot, and behind them was the RSO, which stands for the Reconnaissance Systems Officer, and we'll jump over to the starboard side because that's where the stairs were positioned, and from above here you can see the join line where the removable nose cone would attach to the rest of the plane. Now I'm told that this SR-71 was actually planned to be reactivated in the early 1990s, so it's in great shape. Inside everything is analog and there's no glass screens. This is because it was designed back in the 1950s, but also because analog gauges would better tolerate the dramatic temperature changes. While the dials might have been a reasonable temperature to allow the pilot to touch them, but remember that much of the fuselage would have been extremely hot, so the back-facing part of the dials would have been a lot hotter. Starting down here on the left, and there's a whole lot of circuit breakers, controls for the communication and lighting systems, and 3 oxygen systems, with one being a backup if there was a failure. Here's the 2 throttles, with the first detente starting the engines. Then you push forward as far as it goes for full military power. Then to activate the afterburners, you actually have to lift the throttle up and keep pushing forward until you hit the firewall. As you can see, this weakling was struggling with that process, and the throttles would stay in this position for the entire cruise. While that doesn't sound very fuel efficient, remember that the engines are actually more efficient at Mach 3, as it starts working like a ramjet and the actual fuel use was barely above idle. Below that is the TEB counter that I mentioned before, and there's a number saying how many you have left, starting at 16. If you run out of TEB and the engine stopped, you could not restart and you'd have to eject. TEB would automatically be sprayed in whenever the throttles were moved to engine start, and again to start the afterburner. Here is the exhaust gas temperature, and the pilot could increase this via the switch to activate the backup afterburner ignition system I mentioned before if they ran out of TEB. Here on the left is a landing gear handle and a few other miscellaneous controls for the temperatures and anti-skid etc. This here is a dial to display temperatures for the left and the right equipment bay and the cockpit. The equipment bays should be kept below 140 degrees Fahrenheit and the cockpit around 75 to 80 degrees Fahrenheit. The rest of the aircraft is left to roast by the engines or the aerodynamic heating. This displays the cabin pressure, which was the equivalent of a maximum of 26,000 feet. So that is going to require supplemental oxygen, so both stations were filled with 100% oxygen, which was stored in a liquid form. Moving up, and there's the windscreen, which could get to 620 degrees Fahrenheit during the cruise. It and the side windows were made up of a specially reinforced tempered glass made of multiple layers, and there was also a thin air gap between the inner and outer panes to manage the pressure differential between the cockpit and the atmosphere and avoid transmitting the heat directly into the cockpit. The camera windows underneath were instead quartz, which was more expensive, but the view had to be flawless to avoid distorting the reconnaissance equipment's photos. The pilots themselves could tolerate some mild distortions. There's the regular gauges including the angle of attack, but what's interesting is the airspeed indicator, which would be completely inaccurate at high speed because of the shock waves and other interference across the pitot head, so instead they would use the TDI, the triple display indicator. This included the equivalent airspeed in knots, which is calculated based on the compressibility of air at a known altitude and speed, so it provided altitude and a Mach number too. This dial here is the inlet temperature and came directly from the device right at the front of the engine that I pointed out earlier. The top speed was primarily limited by temperature. In fact, it was 420 degrees Celsius, which is around 800 degrees Fahrenheit. You can actually see a little red mark at the 427 degrees on this dial. So flying above the North Atlantic, where the air was extra cold, you could actually exceed Mach 3.2, but when flying in warmer climates, they might actually hit this temperature limit below Mach 2.9. They say that the airspeed limit was probably around Mach 3.55 because that's where the inlet spike would no longer be able to correctly position the shockwave for the J-58. Now there might be some confusion about the air temperature, as we know it's extremely cold at 80,000 feet. In fact, it's probably around minus 60 degrees Fahrenheit. But remember that once this air goes past the inlet spike and crosses the shockwave, it slows down, but the pressure and temperature increase dramatically, hence why they have to keep an eye on the inlet temperature. This button here is to communicate a problem with the RSO if the intercom does not work. One direction is to alert them to prepare for the possibility of an ejection, and push the other way to tell them to eject. Now, while we consider ejections to be fairly safe, the reality is that a lot of crew members were killed or seriously injured during them, so you'd never want to do one unless you really needed to. Unlike the B-58, this did not have a protective clamshell or an F-111 style pod, and was otherwise a fairly regular ejection seat, so ejecting above Mach 1 would have been very dangerous. The switch was covered so that a simple bump might not result in a catastrophic direction to your colleague. The red light here tells you that they have already ejected. At the front is the attitude indicator. A 1 degree pitch change at Mach 3.2 would equate to 3,500 feet per minute, so you would make much smaller 1/20th of a degree changes instead. Below that is the heading indicator. Further on the right are two columns of engine parameters that you'll see on most jets. Let's talk about the fuel for a moment. Up here is the total fuel amount, which would have been just above 80,000 pounds, which is impressive when the whole plane only weighs around 67,000 pounds. But they could not take off full because the whole aircraft was too heavy, so they would take off partially full and then immediately meet a tanker to fill the tanks. They also didn't want to fill the tanks full on the ground, as that would simply speed up the fuel leaking process onto the ground, so it was better to fill them up once they were in the air and closer to the tanks fully sealing as their speed and temperature increases. This down here are for the separate fuel tanks fore to aft. This here is the aircraft centre of gravity, which you can maintain by moving the fuel between those tanks. Once the centre moves too far back, this switch here can be used to move fuel from the aft tank to the fore tank. This button down here will move the fuel in the opposite direction. Here are the fuel flow gauges measuring in thousands of pounds per hour. In Mach 3 cruise, the fuel flow was barely equivalent of idle on the ground, hence why it was able to maintain such long afterburning cruises. There's two electrical generators working as a redundancy power source, although one SR71B was lost with a double failure here, and the engines were starved as the fuel pump simply stopped. Further back on the right is the autopilot, navigation systems and circuit breakers. There was this flexible reading lamp here, which the pilots could aim in any direction necessary, as remember, at 80,000 feet it could be fairly dark outside, and these obviously flew missions at night as well. Looking up and above at the open canopy, and this is a sunshade which could be positioned around to stop glare from the sun. Remember, at 80,000 feet, the sun's radiation is much harsher and there's no clouds to block it. Now sorry, I didn't film this part very well, but there's also a periscope which could be pushed up several inches to allow the pilot to look backwards. He could do this to observe either engines if there was a problem, to ensure that they weren't leaving contrails because that would be a big hint to their adversary that they were around, and also ensure that the fuel dumping had started and then stopped. And this here is a mirror in front to check out your suit and the connections are all okay. And moving down here is this yellow device, which was the ejection seat handle. Just before we check out the second seat, this black square here is covering what would have been a map projector, which was their primary means of navigation. The whole route of the flight is printed onto a film, which is then projected onto the screen, moving in real time. Let's climb up out of this seat and check out the reconnaissance systems officer positioned just behind. The introduction of this seat was one of the major changes from the A12 to the SR71, as this dramatically reduced the pilot's workload. In an era where many of the systems, like fuel trim for example, all had to be done manually, it would have been exhausting for the pilot to remember everything, and important things were more likely to have been overlooked. They were now able to reduce their tasks by 50%, having someone in the back seat. First thing you notice is how much roomier it is in the second row, likely due in part to there not being a central control stick. Starting on the left are the communication systems, as it was the RSO's responsibility to communicate with the outside world, other than on the ground when the pilot might take over and speak to the ground control directly. On actual missions from bases outside of the USA, such as RAF Mildenhall in the United Kingdom, they were flown in radio silence and takeoff approval was given by the tower via a green light. The radio was used within the United States though. In fact, there was a humorous story told by pilot Brian Schill from a training flight when they were listening to ATC and heard a pilot flying a small Cessna ask the air traffic control for a readout of their ground speed. They replied, 90 knots on the ground. Then a Twin Beach pilot asked for their ground speed, and the response was 125 knots ground speed. Then a Navy F-18 pilot smugly asked for their ground speed, even though they would know that from their onboard equipment. The reply was 620 on the ground. Now, not wanting the Navy playboy pilot to enjoy their day too much, the SR-71 crew decided to join in asking Los Angeles Center, Aspen 20, can you give us a ground speed check? They replied, Aspen 20, I'll show you at 1,842 knots across the ground. Here is more instruments, including the center of gravity, which was repeated from in front, highlighting how important it was for such a long aircraft, and the RSO could remind the pilot if they noticed any issues. There were also these warning lights from the pilot so that they could communicate if the intercom fails, and I went through these in the seat in front. It was important that the pilot ejected first, because if the RSO ejected, and immediately followed by the pilot, they might collide in the air. There's no flight controls back here, so if the pilot passes out, this guy was in trouble. Having said that, if the pilot did have the plane in autopilot, the guy back here could actually control the navigation system manually and potentially turn it back towards friendly airspace. You wouldn't want to eject at Mach 3, so you would want to wait for the engines to flame out, then slow down below Mach 1, and then eject then. The pilot was pretty reliant on the guy back here too, as the navigation systems were all back here. The pilot had the yoke and the compass, but that was about it. The screen at the top here is from the view sight underneath the aircraft. This could be used to confirm their location over known navigation fixes and judge how close the pilot could stick to the centerline during landing and takeoff. In here, and before it was removed, was the RCD, which was the radar correlated display. This system processes radar images and then displays them to the RSO to confirm that the target has been captured. What's interesting is that there would be a 60-second delay from taking the radar image to having it displayed here, so it takes a while to process. More importantly, if the image was insufficient, they could loop around and try again instead of discovering the failure once they were back at base. There would have been a fold-out screen here that would have been for the map projector, similar to what you saw in front. Here you can see the projecting device below it. The screen is bigger here than in front, as this guy needs to know all the more details, specifically including locations of Soviet defense installations, etc. Here on the right were dials associated with the location and the fuel, as well as the RSO would be coordinating the in-air refueling with the tankers. And moving down further, and we see the controls for the astro-inertial navigation system, which was positioned behind the seat with a dome looking up that would automatically track 3 stars, providing the crew with exact positioning plus or minus 300 feet. As remember that this was before the era of GPS. It worked in conjunction with an inbuilt inertial navigation system, so the two work with each other to confirm accuracy. Here's a system removed from this aircraft and on display here, and you can see where it would have been positioned in this footage here. The RSO also had an adjustable map reading lamps, and these would be even more important as they had far smaller windows, as you'll see shortly, to allow in atmospheric light, and down in the center between the legs was the ejection handle. Looking up at the canopy above, and you can see those small windows, and below that was a sunshade which could be pulled up to cover them. There was also a mirror positioned to check their suit and makeup before returning to base. And speaking of that, the pilots wore what was essentially an astronaut suit because of the extreme altitudes that they could have been ejected into. Each suit was made individually based on the pilot's dimensions, and air was directly pumped into it, providing pressure and the correct temperature. This actual aircraft itself had just over 3,512 hours of flight time between 1966 and 1997. It was also one of only 2 SR-71s reactivated in 1995 by the USAF, although the program was cancelled in 1998. By the way, this view from above highlights how wide the chines are. Here we are looking back at the RSO's seat again, one last time, and above him were those 2 windows that we saw from the inside. This aircraft's last flight was on the 30th of September 1997, and it was put on display at the museum 5 years later. Immediately behind him was the astro-inertial navigation system that I mentioned before, and moving back further and then zooming in, we have the in-air refueling receptacle in the open position. Otherwise this would have been covered. It's a little hard to see here, but you can see these corrugations in the skin, and that was to allow for the thermal expansion and contraction during flight. There were 3 variants of this aircraft built. The SR71A was the main production version, and that's what we've looked at today. The SR71B was the trainer version with a raised second seat to improve their visibility. And finally, there was the SR71 C, which was composed of a rear fuselage of the first YF-12A that was wrecked in a landing accident, and the forward fuselage of an SR-71 static test plane. Because it was public knowledge that the Air Force were developing the SR-71, there was no point in maintaining the secret and similar A-12 program, so President Johnson ordered the retirement of the A-12 in 1968. The Corona satellites were in orbit by this stage, and while the images were poorer resolution and older by the time the film was picked up than what could have been obtained by the A-12 or SR-71, they were safer from missiles and less provocative than overflights. As we know, the Cold War was often in a state of thawing and freezing, but overflights were a guaranteed way to worsen the whole situation. While the A-12 was retired, the SR-71 continued in missions in Korea, Vietnam, and the Middle East, but not over the USSR, even though that was the original plan. As space technology eventually improved, this expensive program became less necessary, and the Air Force deactivated the Blackbird in November 1989, with the last flight in 1990. It really was a fascinating aircraft, and I hope you enjoyed watching this as much as I did making it. If you did, please give the video a thumbs up and join the discussion below, and check out my channel for many other similar videos, including tours through the B-58 Hustler, the B-47 Stratojet, B-36, F-117 Nighthawk, and the Spruce Goose here on display at this museum. If you're in the Northwest United States, then this museum should definitely be added to your bucket list. Thanks for watching.